Hello everyone and welcome to lecture. Today's lecture will be about classification of critical points and how we do that for multivariable functions. So I guess the main question that we want to answer today is how to classify critical points. So how can we classify critical points of multivariable functions? This question, what it means is essentially, in the last lecture we went over how to solve for critical points, and this question will hopefully be answering for us how to determine, once we solve for the critical points, if it's a local max, a local min, or a saddle point. And we've seen from the directional derivative and from our discussion about the gradient vector field that if you have a picture of the gradient vector field, you can pretty much almost always, if you're looking at the correct plot, determine whether a given point is going to be a critical point. It's a local min, a local max, or a saddle point. But it turns out that just like in 1D, we'll have a very nice test that we can use to figure out and classify these types of critical points. In general, as long as the function is smooth enough in some sense. So if it's differentiable enough. And like a lot of the theorems, that's kind of the kicker. That's the thing that has to be true in order to apply a lot of these tests, is that your function has to be smooth enough in some sense, or differentiable enough. So the derivative has to exist enough that you can actually apply the test. So let's do some review. We're going to kind of put this in our bubble here, our 1D review bubble. And we're going to look at a function of a single variable. So y is equal to some function of x. And let's say, for instance, that maybe there's a local max right here, the local min right here of the function, and then at some third point there's some inflection point. So at this point x1, we have a local max of the function. It's a critical point because the slope there is 0. Specifically, it's that critical point of type 1, or f prime being equal to 0. Then also at this point x2 right here, the minimum of the function, that comes down and then it goes up like this. You see that at x2 we have another critical point of this function, and this critical point right here is also a critical point of type 1, because the first derivative at this point at x2, or f prime at x2, is equal to 0. And this third point right here is also a critical point. Specifically, it's a critical point of type 1 because the slope at this point right here is 0. So f prime of x3 is equal to 0. These are all the different types of critical points of type 1 that you get for a single variable function. And for each one of these critical points, you'll remember that we have two different ways of classifying the critical point if the function is differentiable enough in some sense. The two different ways that we have of classifying the critical points of this function are called the first derivative test and the second derivative test. So let's review both of these in turn and see why both of them work. So the first thing we should start with is define exactly what a local min and a local max of a function is. You'll remember this hopefully from your single variable calculus class. And I'll just write down the definition so that we can kind of remember exactly what this is. So we say that a function f has a local min or local minimum at a point x star if the value of the function at x star is less than or equal to f of x. So it's less than or equal to the value of the function for all x in some open interval. Around the point x star. So in this example, x2 right here is a local minimum. If you take any open interval that's small enough around x2, say x2 plus delta is the upper bound of this interval, and x2 minus delta is the lower bound of this interval. For any point in this interval, x, f of x is always going to be, the function is always going to be greater than the value at this value x2. So that's why x2 is a local minimum. You have the exact same definition in some sense, word for word, defining a local maximum. Only the inequality becomes reversed. So for a local maximum, so this is the same almost word for word. So I'm just going to denote that here by just saying f has a local, and the only difference is that it's a maximum at a point x star if the value of the function at x star is greater than or equal to f of x for all x in some open interval around x star. And that's evidenced by, say, if you look at this picture, you can again find an open interval around x1. We'll say x1 plus delta, x1 minus delta to x1 plus delta. This is an open interval around x1 where the value of the function f of x is always less than the value of the function at the point x1. So that's what makes that a local minimum. Now, it's not necessarily a global minimum or a global maximum. This is a local maximum, local minimum. They're not necessarily what are called global minimums or maximums, because for this function right here, if you're considering this function, say on the interval from a here to b here, the global maximum of the function is actually this value right here, and the global minimum value of the function is this value right here. So local minimum and maximum are only for, locally around the point. If you kind of look very close around any point, or around a local min or a local max, in that neighborhood that you're looking in, it's a minimum, but it's not necessarily the global minimum or absolute max or min. So when we're doing optimization problems, very often we're interested in solving for that global min or global max. And we'll also see how to figure that out, similar to how you would do it for the 1D case. So that'll be in the next lecture. So the first derivative test says the following for us. It says that we can actually use the first derivative to classify a given critical point. If we know that solving for critical points of type 1 are points where the first derivative is equal to 0, and it turns out that we can use this information to actually tell you exactly what type of critical point that you're dealing with, whether you're dealing with a local min or a local max. So the first derivative test says the following. It says that we suppose f is differentiable on the interval, let's say from a to b, except possibly at a critical point. This can be either a critical point of type 1 or of type 2. Remember, type 1 is where the first derivative is 0, and type 2 is where the first derivative does not exist. The first derivative test tells us that if the derivative of the function is greater than 0 when x is greater than 0, or greater than x naught, the critical point. I'll actually use x star for the critical point. And if it's negative when x is less than this point, then x star is a local minimum. It has to be a local minimum. Because this would mean that the function, as you're going to that critical point, this point is x star, the function is decreasing to the left of that critical point and increasing to the right of that critical point. This is the first statement of the first derivative test. And we have two similar statements that basically apply to the other possible scenarios that we have. The next statement is that if the derivative of the function is negative, or the function is decreasing to the right of that critical point, and it's increasing to the left of that critical point, so it's positive to the left of the critical point, then that critical point has to be a local maximum. because if this is the case, then at this point x star the function's increasing to the left of x star, but then decreasing to the right of x star, which means that this point has to be a local maximum. In the last statement of the second derivative, the first derivative test here tells us that if neither of these things is true, so if the function increases or purely increases or purely decreases, then this point is some type of saddle point, or not saddle point for a 1D function, but inflection point. So the function has neither. So if neither of the first conditions are true, then x star is neither a local min or a local max. So it's possibly some sort of inflection point, right, or other type of point where the derivative, it's a critical point, but it's not a local max or a local minimum. So we've directly seen how this concept generalizes to multivariable functions in terms of the gradient vector. Now we've shown in a number of different examples that, for say, this holds in any number of dimensions, but if you have a critical point of a function of two variables, say you have a function of x and y, you have three critical points maybe. Well, at one critical point, you could have points where the gradient vector sort of goes in and points into the point, but then also the gradient vector here maybe points in, then moves away here, moves away here. If the gradient vector is always moving away from the function at this point, say, it's a local minimum, and if the gradient vector is always pointing in to this point right here, and this is a local maximum of our function. So this would be what the gradient vectors look like for a saddle point, for a local minimum, and a local maximum for a function of two variables. But the idea here is that the logic is exactly the same, and we're seeing the exact same result for the first derivative test. So you can directly take the first derivative test and actually extend this directly using the gradient vector, as we showed before. So this picture shows, right, using, like we said, the gradient vector field, right, so all these vectors here are the gradient vector, but it shows how we can directly extend the idea from the first derivative test to, multivariable functions. That if you look at a detailed enough plot of the gradient vector field for a smooth function, you can directly calculate critical points based on that nice property of the gradient vector that we proved actually in the directional derivatives lecture. But so what it definitely pays to do here is to directly define exactly what we mean by a local minimum, a local maximum, and a saddle point of our multivariable function. Just so that we can, be very, very clear how we're going about in deriving the second derivative test a little bit later on. And I probably won't get into the details of this derivation in this lecture, but I might post an additional bonus lecture where I talk a little bit about it. So we define a local maximum as follows. We'll say let f, this is in general for nd, and we'll kind of look at what this means in 2D. So let f be a function from n-dimensional space to R defined on some region D within the natural domain. Of the function f. The function at some point r star is a local maximum, or r star is a vector, value of f if f of r star is greater than or equal to f of r for all points r, and I'll use the above arrow notation for my vector r here. So for all points r in some open region around r star. So in 2D, I said before that this point right here is a local max, and it's a local max because we can kind of draw a small region around the point, and for any value of the function in any of these points in this region, the value of the function at that point is going to be less than the value of the function here, or f of r star, the black point right here, is going to be less than the points that we're evaluating this at. So I'll color these as gray for any points in this region. The definition of local minimum is almost directly the same, word for word the same, except we have to switch the inequality around. F at r star is a local minimum value of f if f of r star is less than or equal to the value of the function f for any points surrounding r star in some small enough region. So up here in this picture, I said this point right here was a local minimum. It's a local minimum because if we surround this point by a small enough region, this blue region right here, and we consider the relative value of points in this region compared to the midpoint of the region, the value of the function at any of those light blue points is going to be greater than the value of the function at that central point. So therefore this point is a local minimum. This is why the first derivative test really does kind of classify local minimums, local maximums, and also what we've determined to be saddle points. So we'll define a saddle point right now as well. So lastly, a saddle point, or f of r star, is a saddle specifically r star is a saddle point of the function f if for all regions, no matter how small you make the region, around r star, there exist points r1 and r2 such that f of r2 is greater than f of r star, strictly greater than, and f of r1 is strictly less than r star, or f of r star. No matter how close you kind of zoom in around the point r star. And this is clearly evident here for what we call the saddle point right here, because if I draw a small region around the saddle point, do it in gray, no matter how small you make this region right here, there will always be points that have a greater function value than the value at this midpoint, and there will always be points that have a smaller value, lower value than the function at the midpoint. Now, there are many different types of saddles, and when we get to the examples, I'll actually give you a couple examples of standard saddle and also a relatively special, different type of saddle. So what we're going to do now is move back to 1D and discuss the second derivative test for single variable functions, and then I'll briefly discuss how to extend that to multivariable functions. Let's review the second derivative test for single variable functions. So again, we'll consider some function of x and x, so y equals f of x. And this specific function right here looks like it has two critical points, both of type 1, where the slope is 0. And we want to kind of try and remember what the second derivative test tells us and why, in fact, the second derivative test works. So you'll remember from a previous calculus course the idea of a Taylor series of a function. And let's just consider the Taylor series approximation of this function around the point x2, the critical point x2. So you remember the Taylor series approximation of a given function is the following. It says that f, the function in some small region around x2 the value of the function is going to be equal to the value of the function at x2. So if you take x2 and you take some other x that's very, very close to x2, the Taylor series approximation of the function is going to say that the function at x is equal to f of x2 plus the first derivative at x2 times x minus x2. And I think we only need to take it out, we only need to really take it out to the second term, I guess the third term in the Taylor series approximation, which is the quadratic term, to see what we're about to show. But this is the first three terms in the Taylor series approximation of the function. And then we have to add to that always an error term, or the remainder term in the Taylor series approximation, which is going to depend both on, we'll call this R2, depends both on x and on x naught. With the property that R2 goes to 0 very fast. As you get closer and closer and closer to the point at which you're evaluating the Taylor series at, right, the limit as x goes to x2 of this remainder term divided by the distance between x and x2, this limit is equal to 0. And it's x minus x2 squared, because we went out to the quadratic term in the Taylor series approximation. The main idea is that this remainder term goes to 0 very, very fast, faster than quadratic in terms of the distance between x and x2, as that distance gets smaller and smaller and smaller. Right, so if this interval right here is very small, or if the distance between x and x2 is much less than 1, it's very, very small, we have that f of x is approximately equal to the value of f at x2. And if you remember, x2 is a critical point of type 1 where f prime equals 0. The first derivative of f equals 0. So this entire thing is going to be equal to 0 as well. And when x minus x2, or you're very close to x2, this means that f of x is approximately equal to f of x2 plus 0, so I'm not going to include that, plus the second derivative at x2 over 2 times x minus x2 squared, and then the remainder term is essentially 0. So we essentially this thing, because it's going to 0 much faster than this term, when x minus x2 is very small, we have this nice approximation right here. And what that means is that f of x minus f of x2 is approximately equal to the second derivative at x2 over 2 times x minus x2 squared. And then our condition for a local minimum, for x2 being a local minimum, is directly satisfied if a certain condition on the second derivative is satisfied. Namely that, remember we say that x2 is a local minimum if there's an open set around x2, or an interval around x2, such that f of x is always greater than or equal to f of x2. Which is the same thing as saying that f of x minus f of x2 is greater than or equal to 0. So this condition tells us that at a local minimum, for a function that has a second derivative, the second derivative, f double prime of x2, has to be greater than or equal to 0 at the point. Or the function has to be concave up at the point. This is a very, very nice property because it's essentially telling us that for a function whose second derivative exists and is smooth, we can go through and calculate directly the second derivative and use the second derivative to classify that critical point. If the second derivative is positive, then the function is, or that point, the critical point, is a local minimum. And the opposite holds as well. If the second derivative is negative, right, in that for a small open interval around the point, then you have a local maximum. And if neither holds, right, then you don't have a local max or a local min. You have some sort of other inflection point or some sort of other critical point. So the big idea here is that we're going to go through and actually show this and kind of justify. This is going to give us a direct justification for what's called the second derivative test for multivariable functions. Oops, and I just realized I have two small typos here. I'm super sorry about that. This should be x2, because the remainder term in the Taylor series depends on the point of expansion, which in this case is x2 and x, the point that we're evaluating the series at. And then also this should be a strict inequality right here from the second derivative test in 1D. Sorry about that. So what we'll focus on is for functions of two variables, because it turns out that this second derivative test for multivariable functions can be kind of complicated for larger and larger and larger functions. But I will go through and kind of show how to go through and do this and how to think about this in general. So suppose we have a critical point. So a multivariable function and a critical point. Of the multivariable function. We'll call that critical point R star. And specifically, we'll say that it's a critical point of type 1. So because of that, we know that if it's a critical point of type 1, then the gradient of the function f at the point R star is equal to the 0 vector. Just all the partial derivatives are equal to 0. Well, it turns out what we can do is we can do a similar procedure to the one we did in 1D, and it's called the multivariable Taylor series expansion. Of the function f. Now, I'm not going to go over that in this lecture because it's a little bit long, and there's actually some interesting things from linear algebra that pop up when you want to kind of express this multivariable Taylor series in the most simple way possible. But it turns out that this is the key to getting the second derivative test for multivariable functions. And it turns out that the main thing that this second derivative test depends on in the multivariable Taylor series expansion, just like in the single variable Taylor series expansion, is that it's going to depend on all of the second partial derivatives, or the Hessian matrix of this function. So recall that in 2D, the Hessian matrix of a function is the matrix of all of the second partial derivatives of the function. So for a function of two variables, it's a 2 by 2 matrix. This is for a 2 variable function, or in 2D. Now for a 3 variable function, it'll be a 3 by 3 matrix. For a 4 variable function, it'll be a 4 by 4 matrix. So it gets very large, depending on how many variables your function has. And this is one of the reasons why the second derivative test becomes more and more complicated for the higher number of variables that you have, because the Hessian matrix becomes larger and larger and larger. But the main result that you can show using the second derivative, or using the multivariable Taylor series expansion, is the following: that at a local minimum, so if R star is a local minimum, then the Hessian matrix has this property from linear algebra called positive definiteness, or positive definiteness. The Hessian matrix at R star is positive definite, which is a property that any matrix may or may not possess. The second statement is if R star is a local maximum, then HF at R star is what's called negative definite. And then the only other possibilities that you can have if the matrix, the Hessian matrix, is not positive definite or negative definite, is that you could have, say, that R star could be what's called the saddle point. Or, in certain circumstances, for certain matrices, Hessian matrices, you could have that the test is inconclusive. Or it doesn't actually tell you whether or not the R star is a local minimum or a local maximum. So these are the four conclusions of the second derivative test, and it actually comes directly from the multivariable Taylor series. I might include an optional lecture a little bit later on to kind of maybe go over this a little bit more, and in the lecture I'll talk a little bit more about how to actually get the multivariable Taylor series expansion of a function and actually show this for a given function, because it really is very interesting and very kind of a clever use and combination of linear algebra with multivariable calculus. But for now, this is really all that we need. And what you want to think of is that this property of the Hessian matrix being positive definite is kind of like an analog of in 1D. At a local minimum, the second derivative of a function is positive, and at a local maximum in 1D, the second derivative is negative. And for multivariable functions, this is analogous to how at a local maximum, the Hessian matrix has the property of being negative definite. So this is kind of a very, very cool generalization of the result for single variable functions. But let's see exactly how we determine the positive definiteness or negative definiteness of a 2x2 matrix. And this is all we'll probably consider in this course, because determining this for a larger matrix is actually a little bit harder and relies on certain properties of the matrix called, certain values associated with the matrix called eigenvalues, which is a little bit too advanced for this multivariable calculus course. What's really important is how we're going to use this, and this is the following. So the second derivative test for functions of two variables says the following. That the function f of xy and its first and second partial derivatives are continuous throughout some domain specifically. We'll be very specific here, throughout a disk centered around a critical point R naught, which is just x naught, y naught, this is specifically a critical point of type 1, where the gradient of the function at the point is the zero vector. And we have the following four results. F has a local maximum at the point R naught if the second derivative of f with respect to x at the point R naught is less than 0, and the following expression is also less than 0. So this is going to be, I think what I'll do is I'll actually use the other notation that we had, the subscript notation, because it's just going to be a little bit easier to write down. So it's a local maximum if the second derivative with respect to x at the point R naught is less than 0, and the quantity fxx times fyy minus fxy squared. This entire quantity is greater than 0. This is at the point R naught. And the reason being is that this condition right here, these two conditions, tell us exactly that the Hessian matrix so both of these two conditions right here tell us that the Hessian matrix at the point is positive definite. And this is a condition from linear algebra that we're not going to explain in this course because I'm just kind of going over multivariable calculus in the course. But the idea here is that a lot of students wonder where these conditions are coming from for the second derivative test for a function of two variables, and what I've given to you is exactly the reason why. You need a little bit of linear algebra, but it turns out that these two conditions being true at the point give us that the Hessian matrix is what's called positive definite, which is in some sense analogous to saying that the second derivative of the multivariable function is positive. So similar to the condition, in single variable calculus for a single variable function, right? If these two things are true for a multivariable function at a critical point of type 1, we can say that that point with definity is a local maximum, because in some sense the second derivative, or not local maximum but local minimum here. Oh, this is the local minimum, or negative definite. Sorry, I was writing down the order wrong here. So the positive definite was actually correct, but the order that I wanted to write it in was a little bit wrong. So it has a local minimum if this is positive and this is positive. I like doing local minimum first because it kind of gives you, in some sense, it's analogous to the second derivative being positive. So if this thing is positive, the second derivative with respect to x is positive at a point, and this expression right here is positive at a point, this gives us that the Hessian matrix is positive definite, which means that f has a local minimum at that point. Because in some sense, the second derivative of the function, you can think of it as is positive at that point. It's a more complicated property, positive definiteness, but the idea here is that it's analogous to the second derivative being positive at a point. The second result from the second derivative test is very similar to this one. It says that if f has a local maximum at the point r0, if the following is true. If fxx at the point r0 is less than 0, is negative, and if this expression fxx fyy minus fxy squared at the point r0 is also greater than 0. This is less than 0 and this is greater than 0. If these two things are true, so the second derivative with respect to x is negative and this expression right here is positive, that means exactly that the Hessian matrix is negative definite. So these two conditions give us that the Hessian matrix HF is negative definite, which is analogous to saying that the second derivative of the function is negative at the point. So if it's a critical point, then the critical point must be a local maximum. So the third condition is that we can actually definitively say that f will have what's called a saddle point. And for this one, we actually only need to do one check. It'll have a saddle point if this expression right here, fxx times fyy minus fxy squared, is negative. So the saddle point is sometimes easier to check because all we have to do is look at this expression right here, this combination. And the last condition here, the fourth result we can have is that the test is inconclusive or doesn't actually tell us anything about the critical point if this expression is equal to 0. So if the second derivative with respect to x times the second derivative with respect to y minus fxy squared at the point r0 is equal to 0, then we don't actually learn anything from the test. We have to go to some other higher order test to determine the behavior of the function at the critical point. But so these are the four main results from the second derivative test for functions of two variables. And it's important to emphasize that you can also come up with a second derivative test for a function of more than two variables, right? This works for any number of variables, but it's sometimes much more difficult to deal with for higher variable functions. The second derivative test is the more number of variables you have, the more conditions you're going to have, because the harder it is to determine, in some sense, whether the Hessian matrix is positive or negative definite at a given point. Another thing to emphasize and to kind of show is that when you're going through and you're using this second derivative test for a given function, very often you call this expression the discriminant. And the reason why is, in some sense, that it's related to the determinant of the Hessian matrix. So I'll do a little bit of a review here. Remember, the Hessian matrix is the matrix of the second partial derivatives for a given function. So it's fxx, and then fyx, fxy, fyy. And you'll recall, right, that for the function we're talking about, both the second partial derivatives are continuous, all of them are, which means that from the mixed derivative theorem, right, fxy is equal to fyx. This is the same thing as fxx times fxy, fxy, and then fyy. And if you remember, you might not have seen this, but so for any matrix A, this is A, B, C, D, from maybe a basic calculus course or a basic linear algebra course, you will hopefully have seen that the determinant of the matrix A for a 2 by 2 matrix is the product of the diagonals, the product of the first two diagonals, so A times D minus B times C. This is a little bit of a review of how to compute the determinant for a 2 by 2 matrix. For any 2 by 2 matrix. So the idea here is the following, that if you consider the Hessian matrix for a function, and you want to take the determinant of the Hessian matrix, well, the determinant of this Hessian matrix is exactly the product of fxx times fyy minus fxy times fxy, which is fxy squared. So this is sometimes called D, or the discriminant of the function f at the point r0 if you evaluate it at a point r0. So what you're seeing is that the second derivative test depends exactly on this first entry right here on fxx, the sign of fxx at a point, and on the sign of the discriminant or the determinant of this matrix, the Hessian matrix. So in this course, we're only going to go over this second derivative test for a function of two variables, but it's good to see this because these are some ideas that I've shown that kind of generalize to more complicated scenarios in functions of more than just two variables. But in this course, we'll only deal with the second derivative test for functions of two variables. So what I'll do now is go over a number of different examples of how to actually apply this to actual functions of two variables.